So I'm here to talk about a few books by Isaac Newton. Some of them published during his lifetime, some of them published posthumously. He died in 1727, and I'm going to look at some books that deal with pure mathematics, with physics, including his great work Principia Mathematica, originally published in 1687, his great work Optics, which appeared first in 1704, and then a bit later on I'm going to talk about some of the works that appeared immediately after his death. That includes some work on theology and chronology, and then later on in the I'm going to look at some books that deal with the translation, if you like, from Newton's Baroque mathematical notation into the kind of notation that we use today in physics, that are found in a number of books published in the mid-18th century by what we call continental European authors. So I'll start off with the great work, the Principia Mathematica of 1687. Isaac Newton was born in 1642 on Christmas Day in England and some other Protestant countries. In a number of other countries in continental Europe, he was born on the 4th of January 1643, and that's because there was a different kind of calendar used in continental Europe at the time. So most people think Newton was born in 1643. His biological father died before he was born, and his mother remarried when he was 2 years old, giving Newton 3 half siblings. Newton was a very independent young man when he grew up. He was capable of studying and working on his own, and I think that independence fed into his later career and his later brilliance. He went to Grantham Grammar School in 1655, and he lodged in Grantham. He was there for just over 5 years. He was very good at what he did. He spent a lot of time building things and doing other things that distracted him from his work. But when he wanted to, he could come back and he could excel at really whatever it was he wanted to do. And he went to Trinity College, Cambridge in the summer of 1661. And we know that for the first 2.5 years, he was trained or educated in a traditional scholastic context. And then at some point in early 1664, he began to read new works in mathematics and what was called natural philosophy, which is effectively what we call science. And he began to take on board many of the new things that were coming out from contemporaries, some of them English, like Robert Hooke and Robert Boyle, and some of them from people in France and elsewhere, particularly Descartes and Christian Huygens. And he didn't just take these on board, he began to criticize them, and he began to develop and build on his thoughts that resulted from this critique or this examination of contemporary works. And in the middle of the 1660s, at a time when he left Cambridge to go back to Lincolnshire because of the plague, he made fundamental discoveries in mathematics, particularly with the binomial theorem and calculus, and he also discovered the heterogeneity of white light. I mean, all of these were extraordinary discoveries and things that he largely wanted to keep private. The work on optics led to the creation of the first working reflecting telescope in 1668, and in a sense that is what made Newton's name outside of his local environment in Cambridge. But the next year, in 1669, he wrote a work called in Latin De Analysi, on analysis, and this helped him. This was a mark of his brilliance, and it helped him get the position of Lucasian Professor of Mathematics, which he was given in September 1669. He became the second professor following Isaac Barrow, and from that period, 1669 and 1670, he became much more widely known to people in London and elsewhere, and particularly his work became known in the Royal Society. By the middle of the 1670s, Newton was well known as a very good researcher in optics, but not much was known about his mathematical prowess. And round about the middle of the 1670s, he gave up mathematics and science really to concentrate on alchemy and theology, which is an extraordinary thing. I mean, he basically gave up doing mathematics and science, except for the lectures that he had to give as the Lucasian professor. The story goes to 1684 when the astronomer Edmund Halley visited Newton and asked him about what Newton thought about the relationship between the elliptical orbits of planets and the inverse square law, the inverse square force law that was known to govern the motions of planets. People wondered if Newton could offer a proof that elliptical orbits of planets resulted from an inverse square law. And Newton couldn't immediately respond to Halley, but in November 1684 he sent a short paper, De Motu Corporum in Gyrum, on the motion of objects or heavenly bodies in circles. And this became the origin of what 2 years later was the Principia Mathematica, ultimately published in 1687. And Wadham has a number of copies of this work, the first edition being 1687, which I have in front of me, and other works, 1713, the second edition, and 1726, the third edition that appeared a year before he died. Newton has sent his 12-page document essay to the Royal Society at the end of 1684, but he hasn't yet got to the famous discovery of universal gravitation, which will make his name in the published edition. And we know that in the first part of 1685, Newton generalized many of the major discoveries he'd made about the way that objects are related to each other in the local solar system. So those are large bodies in a local area. He generalized this throughout 1685 to talk about all massive bodies in an infinitely large universe. So by the end of 1685, he had this extraordinary thought, which he had effectively mathematized, that every massive particle in an infinitely large universe attracts every other particle according to the product of the masses divided by the square of the distance between them and multiplied by a constant that we now call big G, which in a sense allows one to measure and quantify these relations in standard units. And the book I have in front of me is the book that appeared in 1687, in the summer of 1687. It wasn't unheralded. People knew from late 1686 because Newton had sent the first of 3 books to the Royal Society. The Principia is perhaps confusingly composed of 3 books. So people knew what the general tenor and the general ideas in the Principia were, but still when the book arrived in the summer of 1687, it created a sensation, and in time Newton would become the first scientific genius, a man who had done something that people thought was absolutely incredible. He'd done something that brought together the best insights of people who'd come before him, but also, in a sense, paved the way for the way that the physical sciences would be done for the next 300 years. And I think that was recognized fairly quickly. In the book we have before us, we have on the very front of the book the title in Latin, and it has an imprimatur. It's authorized by the then president of the Royal Society, who is the famous diarist Samuel Pepys. And Pepys's name is exactly the same height, and it's a different font, but it has exactly the same presence on the title page as Isaac Newton. And it gets the imprimatur from the Royal Society in the summer of 1686, but it was published a year later, as I said, in 3 books. And the books are made up, first of all, the first 2 books are essentially mathematical. They deal with various mathematical laws. The first book deals with what happens when you have bodies attracting each other in a non-resisting medium. So in a world where there's no air resistance, or there's no equivalent, there's no theoretical equivalent of resistance. Book 2 deals with Motion, again, it's mathematical. It deals with motion in resisting media, that could be in fluids. Newton's goal in book 2 is to try and show that the current theory of vortices, so the idea that planets are moved around the sun or the moon is moved around the earth due to local fluidic vortices. He wants to show that that is incoherent and absurd, and that will cause him problems later on. But essentially in this book we get the first 2 books being mathematical, and the third book is called The System of the World. And The System of the World is the book that deals with the laws of nature as they are in the world that we see and live in. And Newton's great work, or his great triumph, is to solve some of the problems that had beset people for hundreds or perhaps thousands of years, explaining, for example, the tides. The tides are difficult to explain. People had come before Newton and tried to explain them, Galileo most famously having failed to do so. Newton explained the shape of the Earth. The Earth is an oblate spheroid, he proved, so it's flattened at the poles. And finally, he showed that comets, which had previously been thought to be somehow monstrous or beyond nature, but nevertheless sort of terrestrial local phenomena, Newton showed that they could be susceptible to mathematical scientific analysis, that they travelled in conic sections, that is to say, they travelled in paths that were either circular, elliptical, parabolic, or hyperbolic. And he did things that people, as they said at the time, thought were impossible. They had not even imagined that one could do something like this. So this is, in a few short pages actually, in the final book, the final book on the system of the world is actually quite small. Newton transforms natural philosophy. He solves problems that had beset scientists for hundreds of years, and he paves the way for thinking about how one can deal with problems in the future. So I turn to page 12 in this, again, the first edition, and we can see here we have axioms or the laws of motion. So for the very first time, these are the Newtonian expressions of laws of motion. Other people, particularly Descartes, had expressed laws of interaction. Again, Newton saw Descartes as an inspiration and also as a foil. He followed Descartes in many ways, but also wanted to overthrow the Cartesian system. So in pages 12 to 13, the reader would immediately come across the 3 laws of motion. The first law is on inertia. Bodies travel in straight lines unless they're acted on by other bodies. In the second law, Newton says that a change in motion is proportional to the force of the impressing motion, and that motion follows in the direct line that the impressing motion is exerted. And the third law, of course, says to every action there is an equal and opposite reaction. The third law is one that I think people took much more time to assimilate and to understand in the 18th century. So that's the beginning of book 1, which is this mathematical treatment. In book 2, Newton deals with motion in resisting media, and he kills off, or at least he thinks he does, the Cartesian theory of tourbillons or vortices. And then we get to the book 3, which is the system of the world, which appears on page 401, De Mundi Systemate, Liber Tertius, on the system of the world, book 3. And proposition 7, theorem 7, gives you part of the law of universal gravitation, not called a law by Newton in this book. In fact, the principle of universal gravitation, as he calls it, is never expressed fully in this work, and nor is it expressed as an equation. That has to wait until the work of Leonhard Euler, the great Swiss mathematician, in the 1730s. But in a written form, Newton tells his readers how they can mathematically analyse the forces that make up the solar system and indeed all of the observable cosmos. So Proposition 7, Theorem 7 says that all bodies exert a gravitating power, and that gravitating force that bodies exert is proportional to the mass that they have. And of course Newton has defined for the first time what mass is in the definitions at the start of the Principia Mathematica. I said earlier on that one of the crowning glories of the Principia was the determination of cometary orbits. In the Principia itself, there is a specific analysis of the great comet of 1680. Again, this is something that you can all look up on Google. But when Newton first thought about this comet, it was one whose entry towards the sun had been seen by astronomers in November 1680, and its movement away from the sun had been seen again. Perhaps many people like Newton thought it was a different comet, but a comet moving away from the sun had been seen towards the end of December 1680. It's in that intervening period between 1681 and 1685 that Newton came to understand that this was in fact one comet. And we see in this work an analysis of Newton's work on the comet. There's a wonderful picture, a pull-out picture of Newton's depiction of the comet, and his explanation of it, of course, refers to universal gravitation. People got this book, they bought this book, it sold out fairly quickly. A lot of young men wanted to become followers of Newton. I think it's important to say that for virtually all of Newton's contemporaries, Newton had discovered the way in which God had inscribed a mathematical language into the fabric of the universe. And so there's a strong sense that in reading this book, it's a handbook for people to decipher the Word of God. There's a strong sense in which this is very quickly a kind of holy text that people want to sacrifice most of their lives to understand. And we see that in the years following the publication of Principia, where Newton gets or acquires a number of would-be disciples. Not that Newton liked disciples, but he wasn't that averse to having people follow him when they said that he was a great man. I'm interested in these works. I'm very interested in these works, partly because I could never afford them myself, but because they constitute a massive part of the scientific excellence that, first of all, England and then Britain developed in the early modern period. They're representative of the work of one individual to some extent, but of course he's backed by all the people who came before him and all the interpreters who transformed his work into what we think of as modern classical science or classical physics. But it's particularly significant, I think, to be in this college, because this college, Wadham, was the centre of natural philosophy in 17th century England. And to a large extent, the people who were here and who thrived in the middle of the century were key to the creation of the Royal Society in 1660. The Royal Society became, depending on your definition, the first major scientific society or academy in the world. And the people here at Wadham who worked with the head of house, John Wilkins, in the 1640s and 50s, created some of the doctrines and the style of natural philosophy that would characterize parts of English natural philosophy in the late 17th and 18th centuries. Wilkins himself was an extremely significant figure. Historians in the last 20-30 years have begun to realize just what an influential patron, and not necessarily financially, but in terms of inspiration, he was to a number of people, particularly I think to Robert Hooke, to Christopher Wren, to Seth Ward, who's not particularly well known but was very important at the time, and also tangentially to Robert Boyle. The most important of these, I think, is Robert Hooke, and I'll come on to him in a minute. But Wilkins' work was very important in bringing the Copernican system, that is the idea of a heliocentric system, into the teaching of natural philosophy at Oxford in the middle of the 17th century. And Wilkins himself wrote a book on the probability that the Earth was a planet that travelled around the sun, and also began to think in the 1640s about mechanisms for travelling to the moon, perhaps as a form of sort of imperial expansion. Robert Hooke, who was at Christ Church, came to Wadham and spent a lot of time with Wilkins. Wilkins and Hooke clearly interacted very closely, thinking about what kind of mechanisms would allow people to fly, for example. I mean, there are lots of fantasies of the time. I think that's what drives a lot of science in the middle of the century, but particularly the use of springs to go to various places. Wilkins published a major work, Mathematical Magic, in 1648, where he outlines, it's a bit like an earlier theatres of machines genre, where you've got some sort of fantastic machines, but also some machines that are just about executable, just about possible to put into practice. And Wilkins was incredibly fortunate to have with him this man, Robert Hooke, who was a gifted theoretician, but also more significantly a gifted practitioner, a man who was equally at home talking highfalutin theoretical physics as he was with talking to craftsmen and workmen. And the issue of springs, and we know this from sort of 50 years of Hooke's work up to his death right at the start of the 18th century. Hooke's major obsession throughout his life, I think, was with springs, the development of springs, fantasies of flying. We can see this from his diary in the 1670s. But this capacity, this facility with instruments was key to Hooke's presence, his extraordinarily significant presence in the early Royal Society. The early Royal Society could not have functioned without Robert Hooke, being based at Gresham College in London. But Hooke was the chief operator, he was the chief demonstrator, he was brilliant at devising experiments. And these fed into perhaps the first great published work of English science, which is Micrographia. Of course, the famous work that used a microscope to look for the first time at least for audiences in England and elsewhere, at things like the shape of a louse, the compound eye of a drone, and things that are now famous in the history of science. And Hooke had this extraordinary range of abilities that were encapsulated in that book in 1665. And I think it's really interesting that at the same time as Hooke published that, he was thinking about comets. There was a major comet appeared in 1664 and early 65. There were two comets actually, but they were things that made people like Hooke think about what the causes of comets were, what their paths were. And he gave a number of papers on comets in 1666 during the plague years. And these are exactly, these periods of great creativity for Hooke are exactly the same years of the great creativity that Newton himself experienced and displayed in the middle of the 1660s. And Hooke and Newton would become a kind of yin and yang of English science for the rest of the 17th century. Hooke definitely spurred Newton into doing certain things. He gave Newton great insights into how to think about the analysis of orbital motions. But Newton came to despise Hooke, and there's a great sense, I think, that Newton's power and authority in the early 18th century was used in part to ensure that Hooke's achievements were eradicated, were wiped out from the record, and it's only in the last 20 years that we've been able to fully appreciate first of all, Hooke's own achievements in his own right, but also the real spur, as I said, the real influence he had on Newton. I mean, Newton went a long way before, a long way beyond Hooke. It's no surprise that it is to Robert Hooke in February 1676 that Newton wrote that if he'd seen further, it was because he was standing on the shoulders of giants. And that's true, but Hooke was a scientific giant. This is the third edition of the Principia, one that Newton didn't have a great deal of input into. It was edited by a man called Henry Pemberton, who was a physician, again a follower of Newton. It's the edition that really was the one that was used most in the 18th and early 19th century, or rather translations of it were. So although it's not so different from the first two editions, it actually became the most authoritative version of the Principia. And here there's on the front page, there's a wonderful picture of Isaac Newton based on a painting by John van der Bank and engraved by the great painter George Vertue. People who read the first three editions or the three editions of Newton's Principia that were published in his lifetime would find it very hard to understand what he was saying. First of all, the book's in Latin. Secondly, the book is partly geometrical. It's not expressed in an algebraic form. And some of the things that we believe to be in the Principia, like the law of universal gravitation, they're not explicitly expressed in that book. It took the next 50 to 60 years, in particular the work of Leonhard Euler, Alexis Claude Clairaut and others, to turn Newton's insights into using Leibnizian notation, that's the notation developed by Gottfried Leibniz, to turn it into the kind of notation that we now understand. Key in doing this was a project mounted in the 1730s by Minim friars, Thomas Le Sueur and François Jacquier, who created, as part of a larger project based at Geneva, who created an edition, the first time in a sense that a modern form of notation was used. They created an edition of Newton's Principia, and paradoxically, although they were Minim friars, it's called the Jesuit edition. And this was published between 1739 and 1742 at Geneva. It's known as the Geneva edition. It's profoundly significant for the development of rational mechanics or classical physics in the later 18th century. And it was published in 4 books. So there were 4 books instead of 3, and these books were published over the 4 years from 1739 to 1742. And it's called the Jesuit edition. Le Sueur and Jacquier are the key editors of this work. And the work that I have in front of me is a reprint, again a very rare work, a reprint of this edition from Cologne in 1760, and this is the edition that Wadham College has. Newton was fascinated by light and colour from an early age and made it the focus of his experimental work when he was an undergraduate at Trinity College, Cambridge. And in the middle of the 1660s, he discovered, by the brilliant use of prisms for refracting white light, he discovered that white light is heterogeneously composed of more basic primary coloured rays, that when they're brought together, perhaps using a lens or some other form, they reconstitute white light. And he made a number of important discoveries as a result of this. Practically, the development of his reflecting telescope was a result of his discovery of chromatic aberration. And in the next 30 or so years, he continued to develop his work on optics with a view to, at some point, publishing a major work on that topic. It took until 1704, just after he'd become president of the Royal Society, before his work, Optics, appeared. And surprisingly, it appeared first of all, in English. We have here the first English edition of 1704. It was translated 2 years later into a work that became much more widely read in Europe. Perhaps paradoxically, translating things into Latin made it easier to travel abroad, because English wasn't a dominant language of science or anything else at the time. And another work, the second English edition, appeared in 1717. And this is a major work. It's deeply influential for 18th century optical theory. Newton's work is more accessible. His work in optics is more accessible than the Principia Mathematica. The Principia Mathematica became a byword for difficulty and abstruseness. But optics was very different. There are parts of optics where Newton invites the reader to take prisms and do their own experiments, to reproduce his own work. This particular work in 1704 had another purpose, which was to state or to demonstrate Newton's prowess and priority in calculus. And at the back of the work, there are two mathematical books or treatises. One of them is on cubics, lines of the third order, as Newton calls them, and another one is called on the quadrature of curves, De Quadratura Curvarum, which for Newton was a way, or his mode of understanding what we now call the integral calculus. There's another aspect to optics that is profoundly important, because optics revealed, at the back of optics, Newton wrote a list of queries, which expanded in the Latin and then the second English edition, a list of queries about how the world worked. Newton was adamant in his other work that he wouldn't make conjectures and hypotheses about things. He was keen that these sorts of hypotheses, as he put them, were not mistaken for matters of fact. But in the queries, Newton publicized fairly conjectural, imaginative ways of thinking about the world that he believed in private. Some of them are descended from his alchemical work. Others are more conventionally natural, philosophical, or scientific. But he posed them as queries. So is it not the case that? So that there was a deniability built into these statements. If somebody said, this is what you really believe, which as a matter of fact he probably did really believe them, he could always respond as he did and say, well, I only posed them as questions. So the queries at the back of optics, some of which are on gravity, some of which are on light, some of which are on other aspects, so on life. That's the only points where Newton published anything on biology and life. These are where we get to see, apart from looking at his manuscripts, this is where we get to see what Newton was really thinking and doing in private. As part of the major initiative by a number of people to publish all of Newton's works, the first time that was done in the 1730s, 40s and 50s, we saw earlier on the Le Sueur and Jacquier edition of Newton's Principia, but there were a number of other works as well, many of them excavated from Cambridge for the purposes of publication for the first time. And here before me I have an edition by John Castillon as part of this Geneva collected works, as it were, which is an edition of, or the first book in Castillon's edition of Newton's small works, his opuscula, in mathematics, philosophy and philology. When Newton died in 1727, he had a number of admirers and some members of the family who were very close to him and looked after him. He had lived in Kensington in London for the last 2 years of his life. And the person who took most care of him was the man who had married Newton's half-niece, Catherine Conduit. And the man was called John Conduit. Conduit was a man who had a background in administration, and indeed he would take over from Newton as Master of the Royal Mint almost as soon as Newton died. But Conduit had a great interest in not in making money out of Newton's legacy, but in promoting Newton as a great man in as many ways as he could. One of the key ways in which Conduit thought he could do this was to publish works of Newton that had lain in manuscript for some time, or else to republish works which he felt had not been properly published in Newton's lifetime. One of these was a work that had appeared in 1707, edited by Newton's successor as Lucasian professor, a man called William Whiston, and this was a book called Universal Arithmetic, which was a series of lectures that Newton had given in the 1670s and 80s, and Whiston had turned this into a kind of textbook for students at Cambridge in 1707. And this was originally in Latin. It was translated into English for the first time by one of Newton's gifted mathematical followers, Joseph Raphson, in 1720. And the book we have here is one that was pushed by Conduit to appear very soon after Newton's death, so in 1728. This is the Universal Arithmetic, or a treatise of arithmetical composition and resolution. The second edition, very much corrected, it says on the front page, so you're invited to buy this as a kind of introductory textbook to arithmetic. In the same year, Conduit published something very different of Newton, and something that he himself had invested a great deal of time, and this was Newton's work on chronology. And Newton, something that's not generally known, but Newton had spent much of his life working on pre-Christian chronology, pre-Christian ancient history, and like many scholars of his time, certainly Renaissance scholars onwards, Newton had wanted to try and set all of what was known about pagan chronology in relation to what was known about the Hebrew Bible, so the Old Testament in Christian discourse. And he spent many years on this. He wrote millions of words on it, and a kind of general account of it had leaked to the media, if you like, in the early 1720s. And Newton's work had been attacked by Jesuit critics, and Newton had spent the last 2-3 years of his life furiously writing a response to his critics. He'd never wanted his work or his ideas to be published in the first place. But when these ideas were attacked in the middle of the 1720s, he responded with a series of drafts that were published very quickly by Conduit after Newton died. And so we have here the chronology of ancient kingdoms amended. That is to say, Newton thought he could correct all of the problems that people had found in terms of making them all these stories consistent. And ultimately, all of the pagan or non-Judeo-Christian sources had to be consistent with what he thought the true history of the world was. Most people, including Newton, thought that the world had been created round about 4,000 years before Christ, give or take a few years either side. Another work which was perhaps of most significance to Newton was something that Conduit worked on for some time. He worked on it with another of Newton's distant relatives, and this was on prophecy. This was the analysis of the apocalypse, so works in the Hebrew Bible, Isaiah, Ezekiel, and Daniel, and then most importantly for the Christian tradition, the works of John at the end of the New Testament in Revelation or the Apocalypse. And Newton spent most of his life working on this. He was cautious about giving dates for when the world was going to end, but he did think the world was going to end in about 400 or 500 years after his own time. He was pretty certain that he knew what the structure of the end of the world would be, because it's written, as far as he sees, in Revelation at the end of the New Testament, with with various ways or various nuances that are given to you if you understand Ezekiel, Isaiah, and Daniel properly. But a small part of Newton's gigantic research project was published in 1733 by Conduit. And these two elements, not so much chronology, but certainly the observation on the prophecies of Daniel and the Apocalypse of St. John, which appeared in 1733, these to some extent transformed the ideal of Newton that the Enlightenment and the 19th century had of him. It became more difficult to deal with Newton. Here was somebody who was the founder of reason in the Principia, and to a lesser extent in optics. Someone who'd shown that human beings were capable of understanding this extraordinary world, the language in which God had inscribed the world. But this guy also took very seriously the analysis of Scripture, and not just any old biblical interpretation. This is the most abstruse and perhaps hypothetical, the most peculiar parts of Scripture. Newton devoted his life to doing it. After the publication of this in 1733, it became very difficult to understand Newton, particularly for people in the late 18th and 19th centuries. What was this man? What was his research project? What had he done when he could write the Principia Mathematica and yet also take prophecies as seriously as he did? And that problem, if you like, the issue of trying to work out how one person could do all of these things, is something that, of course, is of great interest to historians today.